Thank you. Thank you very much. Thank you very much for those who organized this meeting and those who made it possible. Thank you all for being here. Thank you for inviting me. I must say, it has been extremely professional the way this has been organized, and I would explicitly like to thank all who made that possible. It was already mentioned that tonight there is a football match. On Wednesday there's a more important one. So the Netherlands will play England. I saw, fortunately, that there are 4 Dutch participants in it. Probably I'm listed as German participant on this one. When it comes to soccer, however, I wear orange, and that will probably never change. So I hope to meet up with some Dutch participants to watch maybe the soccer game. When I submitted the abstract, I gave this as a title on chiral molecules and on laser cooling diatomic molecules, and I will indeed spend the first few slides on giving an overview on what we're doing in the molecular physics department of the Fritz Haber Institute, and that describes that. But then I thought it better to give you a concise presentation on a rather, I think, very interesting topic, namely about thermionic electron emission and associative ionization, and how we got into that and why that is important and why it is of astrophysical relevance, we think. And I saw there's some presentations here also in the meeting that deal with astrophysics, so I hope this is of relevance to some of you. So just, I will say on chiral molecules and on laser cooling, just I will give a very brief overview on what we're doing in Berlin on that. And so the studies on chiral molecules were 3 research groups working on that, and one of the methods we're using is photoelectron circular diagorism, PECD. It's a pure electric dipole effect, and it's a forward-backward asymmetry in electron emission when using circularly polarized light. So here it is. Let me see if this works. So here it's actually shown in a liquid jet. So in a liquid jet, you have molecules, chiral molecules. You come in with light, green, either left-handed or the right-handed circularly polarized, and that leads to more electron yield forward or backward, which you then can measure. So the unique thing, PCD has been studied in many labs these days. But the unique thing we do is twofold. First, we study it on anions. So PECD thus far was studied on neutral molecules that you photoionize, and then the electron leaves, and you see the asymmetry. And it was for a long time a question whether it would work for anions at all. Because if you have a neutral molecule and you photoionize it, the leaving electron has Coulomb interaction with the charged core that stays behind. But if you have a negative ion, I mean, you release the electron and a neutral particle stays behind. And so the question was, is there actually any PECD effect in anions at all? Doing this on anions has the advantage, though, that you can use tabletop laser systems. Photodetachment only takes a few electron volts, so you can use visible or near UV laser systems. And you can do mass selection ahead of time. And it turns out, to give you the short answer, PECD on anions works as good as on neutrals. Okay, so the effect is kind of equally big, and we have been studying that. And the other thing we have been studying this is in liquids, where this picture is from. And there, of course, it's a challenge to do velocity map imaging from liquids. The question is, do the electrons remember where they came from when they have to scatter out of the liquid? And another question is there induced chirality in the first hydration shell around the chiral molecule? So those are interesting questions that we asked. That's one approach, PECD, that we use to study chiral molecules. The other one is with microwaves. So we use microwave 3-wave mixing in a molecular beam. So we have a molecular beam of a chiral molecule. In this case, it's indanol, and we actually make transitions between 3 rotational levels in this molecule. And to get a big effect and to get an understandable and quantifiable effect, what we actually do, we empty 2 of the 3 levels that we want to interact with via optical pumping. And then we induce microwave 3-wave mixing or enantiomer specific state transfer. And then we use laser fluorescence detection of the original empty state to detect the process. I'm not going to tell in detail how this works, but I'm mentioning these experiments because I will be here a few days, and if anybody of you is interested in more details of that, I'll be very happy to explain that in detail and to go over that with you, okay? So that's what we do on chiral molecules. On laser cooling, there are actually two approaches, two groups. One molecule that we're very fond of right now for laser cooling experiment is aluminum fluoride. And why aluminum fluoride? Well, it's first of all, it's a very stable molecule, much more stable than other molecules that people use these days. It has about 7 electron volts binding energy. And it's actually a stable compound. If you heat up aluminum and aluminum F3, it's a stable compound in the gas phase, so you can make quite a lot of it. It has a very strong transition from the ground state, which is a singlet sigma state, to the excited state, which is singlet pi. Lifetime of the upper state is less than 2 nanoseconds, so it's a very strong transition. It's problem being it's in the UV. It's 227.5 nanometers, but there are lasers for that right now. And it's a singlet transition, so that means all Q lines work. So you can go to very high J levels in the ground state. It doesn't only work for the lowest one. You can go to J equals 2, 3, 4, 5, 6, and laser cool on those ones. It's a relatively light molecule, and because the photon energy is quite high, you have a recoil of 3.8 centimeters per second. So that's a pretty big effect. So that's one approach we use. The other approach to study cold molecules deals with dysprosium dimers. This is what Giacomo Valtellino is doing. He wants to create ultra-cold dysprosium dimer molecules and study reactions at strong light molecule coupling. And this is actually triggered to a large extent by Michał's paper, a single author PRL that he published in 2015, that if you have isotope exchange reactions like this one, so you have the 162 dysprosium dimer and it collides with 164 dysprosium atom, you can make the mixed dimer, and the energy difference between these mixed dimers is very small. It's actually less than this 1 gigahertz that is indicated here. And these are energy differences that you can manipulate with coupling to a cavity. That's actually the underlying idea of this project. And then a third line of research we do at the Institute is actually that we have our own infrared free electron laser. And we have our own infrared free electron laser to study properties of molecules. And so this is actually the building in which this thing is. So we cover the full infrared from 3 to 160 microns. We have 2 color operations, and we study with that the properties of clusters and molecules. So we normally mass select the ions, we shape select the ions via ion mobility, we entrain them in a droplet, and then we do IR excitation and ion detection and measure spectra of clusters and molecules in the infrared, which is normally described as the fingerprint spectrum. And it is the fingerprint spectrum. The difference with the human fingerprint being that these fingerprints of molecules you can also calculate. So we can measure the fingerprint and compare it to the calculated fingerprint to find out what the real structure is. So that's the approach we use there. And we do this actually in collaboration with the Radboud University in Nijmegen, which is my alma mater. And we have a joint Max Planck Radboud University Research Center set up for that. What I want to talk with you so all these projects that I mentioned at the beginning, I would be happy to discuss with any of you individually if you want more details on this. What I want to tell you about in the remainder of this talk is about delayed ionization of molecules, or more generally, I will discuss with you molecules that have the very peculiar property that their ionization potential is lower than the lowest dissociation limit. Okay, ionization potential lower than the lowest dissociation limit. It's not for that many molecules, but so the first time we encountered this or had to deal with this was when C60 came out, right? And so this is an old paper in 1991 from Eleanor Campbell and Ingolf Hertel, in which they saw some peculiar things if you ionize C60 with a UV laser. What they saw is that if you ionize with a UV laser, basically you do not produce the ions directly when the UV laser is fired, but these ions are produced on a very long time scale. So it's delayed ionization. And the question is, what is this? Why is this delayed ionization? And in the paper they say, we speculate that this is thermionic electron emission, okay? And so what the idea of that is the following. So C60, of course, has a perfect symmetry. And if you want to break the molecule, the lowest dissociation limit, you have to get a C2 unit out. So you have a C58 and a C2 unit out. That takes about 10 or 11 electron volts to do that. It takes more energy to do that than to ionize it. The ionization potential is 7.6 electron volts. And so the idea is from these experiments, if you actually heat up C60, you pump a lot of photons in, it can just ionize rather than dissociate. At least these two processes will be in competition with each other. And when we saw this paper and we had our infrared free electron laser, we thought, well, if this works, we should be able to heat C60 up with infrared photons on vibrational transitions and bring it to ionization. And so this is what we did a few years later. So basically, it's a very simple experiment. We have an oven here, out of which C60 comes out, and then we have the focused infrared free electron laser interacting with it. And normally with infrared light, you're not going to make a single ion, okay? But if you focus the free electron laser very strongly on the C60, and you have the right wavelength, and I'll come to that, then you indeed see a beautiful mass spectrum. You see almost exclusively C60 plus against zero background. You see a little bit C58 plus. And if you measure the amount of C60 plus ions, and you measure that as a function of the frequency of the free electron laser, you find a spectrum like this, in which you can recognize the four well-known infrared absorption bands of C60, two around 500, and around 1100 and 1300 or 1400. This is a combination band. It's also known as a combination band. So intensities are a little bit screwed in this way of doing it. But what you see is you pump energy in a vibrational mode of the molecule, and you heat it up so much that it then spontaneously ionizes. Well, to get this molecule to ionize, you need to pump in much more than just the ionization potential. This experiment that I did with Gert van Helden at that time, for those who know him. To get this to work, you need to pump in much more energy than just the 7.6 electron volts. To get it on the right time scale, to get ionization and dissociation on the right time scale, or to get ionization on the time scale of 10 microseconds or so that you can measure it in the lab, you need to put in about 40 electron volts of internal energy. Okay? So what that means is that a single molecule needs to absorb about 600 infrared photons. And it does, right? I mean, a single molecule absorbs 600 photons, heats up. This energy is in the wrong modes, it's in vibrational modes. Phase space is huge. It needs to get its act together and give it to this one electron that's going to leave. And so the way it works is just you excite on part of the pulse, and then it relaxes, and then the next pulse of the free electron laser comes, and you gradually heat up the molecule until it ionizes. And of course, in this process, the frequency shifts slightly because the molecules get hotter. And if you indeed chirp the frequency of the free electron laser over the pulse, so the pulse of the free electron laser lasts several microseconds. If you chirp from 525 to 510 over the pulse to stay in line with the resonance of the molecule that gradually heats up, you can do this very efficiently, and you can make a lot of ions. And Boris Sartakov is the one who helped us to model and to understand this. So this is a very peculiar property of C60. You can pump in many photons, and you can learn about the infrared spectrum in this way. If you wouldn't know it before, you could just measure the infrared spectrum in this way. And then we were wondering, what other species do this actually, right? And so there are many more very strongly bound clusters that have this property, that you can heat up and with infrared photons, and then they can ionize, and ionization is more efficient than dissociation. And for instance, it also works for clusters like titanium carbide. So titanium carbide makes these so-called nanocrystals. So the Titanium is the blue ones on the outside. So this is titanium 14C13. So this is 27 atoms. It's a 3 by 3 by 3 cube, right? And you can make a 3 by 3 by 4 cube and a 4 by 4 by 4 cube and so on. And these are very strongly bound. And if you irradiate it with infrared light, it can dissociate, but it can also ionize. And if it ionizes, you can detect these really completely background free. And you get very clean mass spectra. So what is shown here is two mass spectra. One time the laser is at 7 micron. There are special types of small titanium carbide clusters that have a different structure, and they show resonances at 7 micron. If you go to the nanocrystals, the 3 by 3 by 3 and the bigger ones, they all show a resonance around 20 micron. And if you fix the laser frequency at 20 micron, this is kind of the mass spectrum that you get, and you can recognize these different clusters. For titanium carbide, it's not so nice because titanium has many isotopes. And so that's why the distribution gets always relatively broad. In addition, the mass of the main isotope of titanium is 48, which is 4 times 12. So it's a little bit inconvenient if you want to do this. If you do the same thing, it also works for vanadium carbide. If you do the same thing for vanadium carbide, so we do laser ablation of the metal, we make a beam out of it, we have some CH4 or some other carbon carrier in there. We make these clusters and we just ionize them only with a free electron laser. If you do that, you see this lower mass spectrum. If we ionize with UV laser, we see kind of a lot of peaks. If you ionize it with infrared, you just see this lower mass spectrum dominated by the 3 by 3 by 3 cube and by the cube with the missing central carbon atom. So that's actually, these are 2 peaks. But in addition, you see all these higher max peaks, and you can uniquely identify these as nanocrystal structures. You can really learn about how these things form. And the nice thing is, you only see those that are extremely stable. You only see those, and those are normally the ones you want to see, right? You see those that are extremely stable. You see those that undergo this process. Back to titanium carbide. When we looked at titanium carbide, we were actually hoping that if we look at the different cluster sizes, that maybe we see a shift or some change when the clusters get bigger or whatever. And these spectra might not be the most beautiful, but what they certainly show is there is a strong resonance just below 500 wave numbers. And when the cluster gets bigger, it basically stays there. I mean, so all clusters kind of have an absorption around 500 wave numbers or just below. And so we were discussing this, and then we got a visit in the lab of Xander Thiele and Sanlu Alamandola, so two well-known astrophysicists. And they came by in our lab to discuss experiments we were doing on PAHs. We were measuring infrared spectra of polycyclic aromatic hydrocarbons because they are thought to be carriers of the unidentified infrared bands. And so they came actually to discuss that. And then during lunch, they asked us what other experiments are you actually doing with the FEL? And we said, well, we're also looking at these strange things like these titanium carbide nanocrystals. And then Xander Thiele said, well, that's quite interesting. He said there's some puzzling thing with titanium carbide in astrophysics. And he said that if you look in the Murchison meteorite, this is one of the very well-studied meteorites. So in the Murchison meteorite, they are carbonaceous particles, carbonaceous chondrules, micron-size carbon particles. And he said when we look at those under the transmission electron microscope and we analyze these carbonaceous chondrules, we find that the nucleus of these things is almost pure titanium carbide. Every now and then also zirconium carbide, but it's almost pure titanium carbide. And it's really not understood why that actually is, because there's not that much titanium around. And but this is just an observational fact. There's titanium carbide in the nucleus of these things. And then he said, we think we know where these come from, and they come from post-AGB stars. So these are stars like our sun at the end of their life. And he said, if we look actually in the region where this comes from, we see a very strong emission around 21 microns. And he said, maybe that's actually titanium carbide, what we see there, right? And I said, well, 21 microns, that's not where our cluster is absorbed. They absorb at 20.1 microns, not at 21 microns. And he said, well, but let's look at that. We'll send you a spectrum. And so then few weeks later, Xander Thielen sent us the spectrum that they measured from these regions. It's called the 21 micron mystery band in astrophysics, okay? And this 21 micron mystery band, the measurement is the upper curve here. And this is what they observed when they look at interstellar emission. The lower curve here is nothing else but the spectra that we measured of the nanocrystals in the lab, just all sizes added up, okay? So the one is kind of a hot thing cooling down, seeing an emission. The other is a cold thing heated up, what we see in absorption. And of course, it's only a single peak, and it's only one feature. But the peak is at 20.1. Also, this one is at 20.1, not at 21. It's the first astrophysicist measured it like that, but it's at 20.1. And we then wrote a paper together in which we said, well, maybe there are titanium nanocrystals in interstellar space, right? I mean, so, and again, based on one line, that's difficult, but the main thing that we said in that paper at the end is that it is important to realize that these titanium carbon things can undergo thermionic electron emission. And I'm going to read this. The last paragraph of the paper that we wrote said, we emphasize that thermal electron emission may be essential in the formation of such small clusters. When a growing cluster undergoes a collision with either a carbon or a transition metal atom, the binding energy of this atom has to be released from the collision complex. This is always what needs to be done. This can either be a third body, but in low density environments, this usually happens by radiative relaxation. Radiative relaxation, however, is not very efficient, and the transient collision complex will usually dissociate back to reactions. In species that can undergo thermal electron emission, on the other hand, an electron can be emitted, and it can stabilize the cluster. The resulting ion is stable toward dissociation. It can recapture a free electron each time I have an opportunity to radiatively cool. So we claimed in this paper that the fact that these species undergo thermionic electron emission is the reason for their existence, and is the reason why they find it in the nucleus. Okay. The puzzling thing was, I mean, we know this for titanium 14C13, so this is still pretty big ones. How does this process start? And so we left it at this. This was 2000. This was the year 2000. And then, only very recently, a few years ago, I realized that there are also diatomic molecules that have this property. And I think that's really interesting, because then you start thinking, okay, maybe they're essential in forming new species. So there are diatomic molecules that have the unusual property that the ionization potential is below their lowest dissociation limit. I asked many spectroscopists the last years who visited our lab, I asked them whether they knew about diatomic molecules that had an IP below the dissociation limit. And nobody said they knew about this. They all said, I mean, no, it doesn't exist, or must be very strong bound, they're very strange, right? But they do exist. And the thing is that these molecules can be produced via associative ionization. Two atoms can just come together and form an ion and an electron. No third body needed, right? So you can form them very easily. And if you look at literature values, which species can do that, for which the reaction metal plus oxygen, because with oxygen it works very well, makes an ion, a metal oxide plus an electron. You see that if you use titanium, then it's near thermoneutral, but this thing is really exothermic if you use yttrium, zirconium, or lanthanum. So not your usual atoms, but for these it is really exothermic, so you can easily form those. This process is called associative ionization. If I look how many people know about or use associative ionization, and I look for articles with associative ionization in the title. I did this last week, okay? And I plot that. So it's the number of articles is the bars, and the blue is the number of citations. This was peaked in the 80s. And it's basically back to zero right now. And the associative ionization that they studied in the 80s, chemists call it chemi-ionization, okay? The associative ionization that they studied in the 80s was basically between an atom and an excited atom. When they made the first sodium mods, they saw that the ground state sodium and the excited state sodium interact, and they can make a sodium dimer ion plus an electron. That's also called associative ionization. It's also called associative panning ionization. But I'm talking here about associative ionization of two ground state atoms, right? And it's really a process that is hardly known. This paper came out a month ago. In May it came out, so almost 2 months ago, in Nature Physics. It's a review article by Marcus Dye, Stefan Willits, and Joas Hekka-Denschlag about ions, how to make cold ions, and how to use that for cold ion physics. They made this figure in there, and I'm sure this is figure 2 from their paper, formation processes of a molecular cation, and I'm sure they thought very long about this figure, right? And it's a beautiful figure. It says how you can make this ion, this molecular ion. How can you make that? Well, you can start with the molecule and do photoionization. You can start with the molecule and the charged atom, and you can have charge transfer. You can have a molecule and a metastable atom, and then you have panning ionization. You can have substitution reactions. So you start with a neutral molecule and an ion, or a molecular ion and a neutral atom. You can have atom-atom tree-body recombination. You can have radiative association, and you can have photoassociation, right? I mean, they really thought about this very carefully. There's no mentioning of associative ionization. So associative ionization is there, right? I mean, you can't just have two atoms and you can do it. And you can do that much more efficiently. So the claim is, not too many people know about associative ionization, or it has almost been forgotten. And so we then started looking, this is very recent work that we did, on dysprosium oxide. It's one of those other species that is predicted to have an IP that is lower than the dissociation limit. And so, so this is schematically shown here, right? The molecule is supposed to have a ground state that has a dissociation limit that's above the IP. And we were wondering how accurately can we spectroscopically determine this? Can we spectroscopically determine where the IP is and where the dissociation limit is, and how precise can we do that? And some optical transitions from dysprosium oxide are very well known. They're reported in the literature, and it goes to a transition that is to an electronically excited state that's at 17,056 wave numbers. These states are so complicated that they don't have the normal spectroscopic label. You name these states by the energy and wave number divided by 1,000. So this is state 17.1, because it's around 17,100 wave numbers. So the only thing you know is what the omega quantum number is, which is 7. But so this is known. The lowest rotational level in dysprosium oxide is J equals 8. Okay, so you go from 8 to J equals 7 here in this state, and if you do that, actually it's a V equals 0 to V equals 0 transition. All isotopes, there are several main isotopes, they all fall on top of each other. We fix the one laser. We fix on the P8 line. This is this red. Okay, how can I do this here? This is this red frequency. This red frequency here. I don't know how this works. Okay, this red frequency here. That's the frequency of the first laser, and then we scan the second laser in the same range. And what you then see is that for the 161 dysprosium isotope, coincidentally, this first laser already brings you to this level. They just fall on top of each other. And for the 161 isotope, with one laser, it's resonant with this transition and resonant to some higher state, which we call 34.1. And we know this is a J equals 8 level. So in dysprosium oxide, we can prepare molecules exclusively 161 dysprosium oxide in this level. And from there we can look what is actually happening in the region around the IP and around the dissociation limit. Our work was triggered by the fact that last year a paper came out by the group of Peter Amentrout, who actually claimed the opposite, said the IP is actually higher than the dissociation limit. And with a very high precision they claimed that. Well, this paper is just wrong, okay? So this is not correct, but this was a trigger for us to look into that. Starting from this single level in 161 dysprosium oxide, you start from a single quantum level, then and you scan the laser around the IP, this is what you see. So it's chaos. I mean, this molecule has very many electronic states. It's very complicated. But we know that this is the ionization energy, and we know that from Rydberg series that we see here. We see beautiful Rydberg series that we see converge to the ground state of the ion, but you would not recognize the IP from this measurement here, right? But it is this red line, and this is where we identify the dissociation limit. Why do we identify the dissociation limit here? 2 reasons. One is that after this there is a gap here, where these are the 3 limits of the ground states of oxygen, the oxygen atom. And there's a gap here. And from here on, we see that the width of the lines gets broader. So these lines here, they cannot dissociate. They can auto-ionize, but they cannot dissociate. Above here, they can auto-ionize still, but they can also dissociate, so they get broader. Why do you see this? Why do we see this gap here? Well, our rationale is that we see this gap because we have these 3 limits to oxygen, and if you have many states converging to these limits, in dysprosium oxide, to each of these limits, 39 electronic states are converging. Okay, and of course, if they have the same symmetry, you get avoided crossing, and in this region, you will not have levels. So it's this gap that is kind of indicative of what is happening. And I'm not going to go in. This is the work of the people involved. So it was actually triggered by Giacomo's desire to study dysprosium dimers, and got us sidetracked to dysprosium oxide. I'm not going to go in detail to this. This is details of the Rydberg series. This is details around the IP. But we very precisely determined where the ionization potential is, where the dissociation limit is, and that in this molecule really the ionization potential is lower than the dissociation limit by 0.08, very precise electron volts. Okay, this means that you can very efficiently make cold ions. If this is the IP in a field of 1 volt per centimeter, this is the IP in 0 field. If I excite on this line here, right, just above the IP, these are all resonant transitions in a molecule. They cannot dissociate. You can, with 100% efficiently, turn a neutral molecule into an ion, which is state selected. It can only be in the ground state. Energetically, it cannot be anywhere else. So this really triggered us to think about this and to ask more generally, how important is associative ionization for molecule production? So again, normally you need collisional stabilization or radiative stabilization to do this, but if 2 atoms can just form together and make an ion, this is extremely efficient and a way to produce them. And normally, if you make an ion, the ion gets killed by the reverse direction, by dissociative recombination. You have an ion and an electron, and it goes in this direction. But for these molecules, that's endothermic. That doesn't happen. So these ions are extremely stable. And so we were wondering, how important are they? And so I was looking in the literature, actually, what is actually known about zirconium monoxide and those kind of molecules, because these are predicted to do this. So I Googled for zirconium monoxide, and then I found this on Wikipedia. I really found it on Wikipedia. It says on Wikipedia they're S-type stars, and S-type stars are called S-type stars when the optical absorption is dominated by zirconium monoxide. Oh, that's kind of strange, right? I mean, so they know this for 100 years. And so it's dominated by zirconium monoxide. S-type stars are kind of, again, stars like our sun in the late stage. They have a C to O ratio very close to 1. And then I read this further, and then it says S-type spectra also show other difference to those of other classes that are related to it. Namely, the stars in front of them have titanium oxide, and the ones after it, they have yttrium oxide and lanthanum oxide. They're the only ones that are mentioned, right? And then they say there's some peculiar thing, vanadium oxide are absent or very weak, that they don't understand, okay? Well, it turns out that exactly lanthanum oxide and yttrium oxide and titanium oxide and zirconium oxide you can make via associative ionization. Vanadium oxide you cannot make via associative ionization, that is, it's endothermic by 0.7 electron volts. And so we thought, I mean, this must be the explanation why they see this. So then I didn't want to rely on Wikipedia only, so I looked in a little bit more detail how they actually do this and how they classify stars. And this is a paper from 1980. This is kind of an accepted classification of stars in this range. The molecules that I mentioned here are titanium oxide, zirconium oxide, yttrium oxide, and here is lanthanum oxide here on this side. And these are stars in their evolution from top to bottom, and their C over O ratio changes. So these are stars that have a C over O ratio very close to 1, but as soon as it approaches 1, you see these changes going from titanium oxide to zirconium oxide and so on, right? And they don't really know why it changes the way it does, but this is observationally done. And so then we looked at what is actually known nowadays about these molecules. And these are just, for these 4 molecules, titanium oxide, yttrium oxide, zirconium oxide, lanthanum oxide, here is listed what their ground state is. Here is listed very precisely nowadays how good their dissociation limit is known, how good their IP is known, also for the ion, and also dissociation for the ion. Often the difference in dissociation limit for the ion and the neutral is better known than either one of those, so that's why this list is there. But what's also measured is for these species, this is the associative ionization rate. This is how efficient you can actually make the ions via associative ionization. And these are between titanium oxide and lanthanum oxide a factor 200 different, right? I mean, the other differences are not so big. So then we said, how does it actually work? So this is the simplest model you can take. So let's assume we can make the metal oxide ion via associative ionization with a known rate constant, namely this measured rate constant in the lab. How can I destroy the ion? Well, not so I can destroy it via oxygen abstraction with carbon atoms. So carbon, the CO bond is the strongest bond there is, 11.1 electron volts. So when it collides with a carbon atom, it can go back. And so under equilibrium, you get this very simple expression with a known ionization, associative ionization rate and oxygen extraction rate, where this rate we just take as Langevin. I mean, I think everybody will assume this Langevin. You can write this in terms of the total number of metal atoms and MO+, kind of reorganizing this. And then you get this expression where the F here stands for the free oxygen atoms and the free C atoms, because only those can interact. And most of the C and O is bound in CO, in the CO molecule. If you just use this expression and you plot what you would expect as a function of CO ratio, you get this. So only when the CO ratio is less than 1, you have more oxygen than carbon, and only then you have free oxygen, and only then you can make these oxides, right? So this is what you would expect for all of them if this expression holds. Well, then we said maybe this is too trivial. There will probably always be a small fraction of the CO that's photodissociated. There will always be a small fraction that is available kinetically as free C and free O. And we take this fraction as 10 to the minus 3, so really very small. We take that fraction as 10 to the minus 3, and then you can write the same expression like this in terms of this fraction alpha. And if you then plot it, you get these curves. And what you then see is that there's a huge difference in how these behave, in particular around CO equals 1, namely those that have a high rate constant, a large rate constant for associative ionization, increase extremely fast, and the others slower and slower. This is all normalized to 1. The normal abundance of titanium is much bigger than of the other ones, but it does explain that titanium oxide you only see is going to dominate. Titanium oxide is only going to dominate for relatively low values of C over O, so in this range. And the closer you come to 1, the more the yttrium oxide, zirconium oxide, lanthanum oxide is going to dominate. And really it can explain basically all the observations that has been made. This of course is an absolutely trivial model, but fact of the matter is that this reaction is not included in the whole reaction mechanism that they have. And so this is a plot that shows the abundance of the various elements on a logarithmic scale in the sun. The sun has a C over O ratio of 1/3. So there's much more titanium than there is zirconium or lanthanum. But in these stars, when the CO ratio is close to 1, they are somewhat enriched in lanthanum and zirconium. Also, that can also be a factor 10 relative to these numbers. Okay, but what is interesting is they have always been puzzled, why don't we see vanadium oxide? Because vanadium is more abundant than yttrium or zirconium or lanthanum by orders of magnitude. They have not seen it, and I think they have not seen it because it's endothermic by 0.7 electron volts. So this reaction will not run for vanadium oxide, or it will run very badly. They have also not seen boron oxide, which is another puzzle to them. Boron oxide actually has a higher dissociation limit, so you would think it is very stable, but it has such a high IP that indeed it cannot do this process. Okay, so bottom line, and it brings me to the end of my talk, is that I showed you that infrared spectra of strongly bound species can be recorded via thermionic electron emission. I showed it on C60 on the crystals. You can use, if you have these molecules that have this property, you can produce cold molecules via auto-ionization. And I showed it for dysprosium oxide, but it, for instance, also works for thorium fluoride, which is one of the candidate molecular ions for EDM experiments. And I think associative ionization can explain the observed trends on the abundance of titanium oxide, yttrium oxide, zirconium oxide, and lanthanum oxide in these stars. And it can explain all kinds of observations. They have seen large variation in the abundance of zirconium and lanthanum when stars are very close to a CO ratio of 1. They have not seen vanadium oxide, and they have not seen barium oxide. So our call on the astrophysics community is simply to include associative ionization reactions in astrophysical models, because we think they are very essential and they can explain a lot of the details. And now I stop. Thank you.
Thank you very much for perfect timing. Now we have lots of time for questions, so maybe you.
Thanks for the excellent talk, Gerard. So I'm wondering, in the usage of this to ionize the molecules in your spectroscopy, have you thought about maybe the production rates being affected by some sort of Rydberg-style blockade effect? Because when you ionize, you would expect a neighboring molecule to be off resonance, or is the electron around to screen this, perhaps? I wonder if you've thought about this physically.
Yeah, so I think, I mean, the way when we discuss this behavior in stars, right? I mean, that's actually in regions where the density is so low that we would call it extremely good vacuum, right?
Sure.
So we're talking about 10 to the 4, 10 to the 5 particles per cubic centimeter. And that's, by the way, another reason why we think it is so important that these reactions are included, because these are two-body collisions, right? You don't need three-body or whatever. That's not going to happen there. Your question might be relevant if you want to make very many ions, right? When I say you can use it to make very many cold ions, you might indeed quickly be in that regime because the process is so efficient. Yeah?
Right.
Well, then you have to tune it down, reduce the laser intensity or whatever to make it less. But in that sense, you might quickly be in that regime. In dysprosium oxide, there's this double resonance for the 161 dysprosium oxide, and then you go to this state just above the IP. It's all allowed transitions between electronic states with known J levels and selection rules, and they're very strong. So you can really 100% from the ground state J equals 8 bring it to the ion. And that might be too many, and you might see these blockade effects and so on. We didn't look at that, of course.
Yeah. No, I'm just wondering.
Yeah.
Thanks.
Yes, please.
Yeah, thank you for the very interesting talk. I was wondering, like, if you use this to make cold molecular ions, what would set the limit for the temperature which you get? Is it the electron recoil, or?
So in this case, I think the limit for the temperature is set by the temperature you have in the neutral molecular beam to begin with, right? I mean, basically, okay, so in the case of dysprosium oxide, you're helped by the fact that the lowest J level in the ion is 7.5. The next J level in the ion is 8.5, and the separation between those levels is 6.5 wave numbers, okay? So if you are within 6.5 wave numbers above the IP, energetically, you can only make the ground state. The recoil of the electron can only be this 6.5 wave number then, right? Not more than that. And in the end, translationally and so on, it will be determined by how cold you had the neutral beam to begin with, which in our case is not particularly cold. It's a Kelvin or something, right? I mean, so it's just coming from a laser ablation source. Yeah.
Next question.
Beautiful presentation. I am not really surprised to see that for boron oxide you have this high ionization potential, because actually boron is an electrodiffusion system, and therefore when they attach oxygen is very difficult to detach that. But I was wondering all the time what would happen if you move to the right of the first row, for instance. Another monoxide could be nitrogen oxide, and probably in that case the thing could be different.
So I did mention this paper from Schofield in which these values for associative ionization are, okay, and that paper I think it's a wonderful paper. This paper is written by Keith Schofield. He passed away 2 months ago. I didn't know him. He worked his whole lab in Navy labs and in Army labs in the US. And he wrote this paper when he was 68. When he was 68, when he retired from the Army, he got a professor position in UC Santa Barbara. And I think this paper is his accumulated knowledge of what he learned and investigated, classified work during 40 years in the Navy and the Army. He refers to 2 reports that have appeared that he co-authored by himself, single author, 100 pages, in which all the thermochemistry of these reactions is gone. He was interested in combustion, and he was interested in stable ions. And he calls it, this is the title, an overlooked series of gas-phase diatomic metal oxide ions that are long-lived. And there are 18 of them. And this is the table. So this is the table that he gives. And this is actually the reaction that counts. So this is the upper value, is the value in for the delta H in kilojoule per mole. When this is negative, then the reaction goes. Okay, so it goes for scandium. That has also been observed, and cerium has also been observed. So scandium, titanium, yttrium, zirconium, lanthanum, hafnium, cerium, praseodymium, neodymium. And then, well, you can see 18 do this. He doesn't give error bars here. In the paper, he does give some error bars. All the numbers that he gives in the paper are correct and consistent with the more recent measurements within his somewhat larger error bars. And so he knew about this. And he knew this is some forgotten science. And these things are important.
Thank you very much.
So here you can see when you go to the right what happens, right? I mean, that's basically the answer to your question, yeah. But this paper is worth looking at.
More questions? Maybe I can ask about Fullerene, because like the space of rotational state is huge, right? And you are pumping several excitations. So what about kind of steering in this huge Hilbert space by, I don't know, shaping these pulses, or I mean, could you somehow, make some steering there, or maybe looking for quantum scares or things like this somewhere in this huge space?
So if you calculate for C60 the vibrational density of states at a total energy of 40 electron volts, it is the staggering number of 10 to the power 63 per wave number. Okay, so this is humongous space, and I don't know how to steer in that space. How to do that? Strange things have been observed. Strange things have been observed that their structure in these delayed timers is not purely exponential. If you can see some structure in there. It seems to be that the triplet state is involved at some point. So maybe you can do it, but it's.
I would expect some complex many-body physics with one
body,
right? So
yeah.
with this huge space. Okay, do we have the possibility for one last question? Yes, Wojtek.
Thank you. I wanted to ask about the opposite process. So opposite to associative ionization would be dissociative recombination process, right? So for this molecule, what you are showing shouldn't be like this opposite process also like more efficient than regular molecules?
No. So these molecules for these molecules, the dissociative recombination is endothermic. So that's why that doesn't happen. I mean, if the one direction is exothermic, then the other direction is endothermic, right? And so normally the molecular ions are destroyed by dissociative recombination with electrons, but these ions are not. And this is actually that's why Schofield had that title of his paper, an overlooked series of metal oxides that are long-lived, and they find that they are long-lived in combustion processes, right? And so that's why so these ions are long-lived because they cannot recombine. You can form them via a two-body reaction extremely efficiently. It works for all these oxides, these 18. It also works for some fluorides, right? And so there are some species that do this, and I think it's a very important process. And so, I am biased. I'm just excited about this because we're doing this during the last half year or year. So that's why I also thought to tell about this. But I think it's an important topic that is indeed a little bit overlooked. And that word overlooked I take from Schofield's paper.
Okay, so let's thank once more for Gerard for